Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 2, Part 2 Supplemental. So while this video is not required as far as watching it, the information in it is required to be known by you. So you do need to know how to do Taylor's expansion and how to use the remainder expression as well. So this is Lecture 2, Part 2 Supplemental, and we'll call this video 4C. So again, we're going to cover Taylor's series in detail, do some examples, so I hope you enjoy the video. Let's discuss Taylor's expansion, or Taylor's theorem, or Taylor's series. Those are the commonly used expressions for Taylor's result here. So we're going to start with a definition. A function f of x that has derivatives of all orders at x equals a can be expanded by the following Taylor series. Now, what this means is that at the point A, then f of a is continuous. Because in order to be differentiable, you have to be continuous. You can be continuous and not differentiable. If you remember the absolute value, it has a sharp point here, and so the limit in this direction is -1. That's the slope of that line, and the limit of the slope in that direction is +1, and so they're not the same. And at the point, of course, it's 0. So that's not differentiable, but it is continuous. So remember, functions have to be continuous to be differentiable, or if they're differentiable, they are continuous at that point. Okay, so here is the notation for the Taylor's expansion. This is very important. Please add it to your formula sheet and understand how to do it. So there's a few things we have to note, that when we take the 0th derivative, that's defined as, I should put that, so it's defined as the original function. Okay, so f to the 0th derivative is just simply the original function. Okay, so if I is equal to 0, then I factorial is equal to 1, because that's, or I factorial, that's 0 factorial, and that's defined again as 1. So that's something you need to know. Remember, we can never divide by 0, so and we don't have any limits here, so we can't absolutely divide by 0. So 0 factorial, remember, is 1, not 0. So please don't make that mistake. That's a bad mistake to make. Oops, wrong one. Now, so we have the function, the derivative of the function, the ith derivative, at the point A, at x equals a. Okay? And then we take x minus a raised to the ith power, and the whole thing is divided by I factorial. So if we start with I equals 0, let's see how this looks. So that means we have the 0th derivative, and that's just f of a down here, and divided by 0 factorial, which is 1, and then we have x minus a to the 0, so x minus a to the 0 is equal to 1. Okay, so any number except 0 raised to the 0th power is 1. Okay. Now, we go to the second one. So now we have I is equal to 1, so we have the first derivative of f at a, and that's here. Then we have x minus a raised to the I equals 1, and then 1 factorial on the bottom, so that's just 1. Notice I did not write 1, okay? And I did not write 1. I mean, you can do that, but then you need to clean it up and make it look like we would want to use it. We don't need multiplied by 1. That doesn't do anything. It's not informative, okay? So we want this in a final form that is clean, okay? Now, so for the first two terms, you got f of a plus f prime of a times x minus a, and then we have the resulting, we have the factorial, and we have more terms, okay? So when I equals 2, we have the second derivative, again at a, and divided by 2 factorial, which is 2 times 1, which is 2. Okay, and so I've just put that there. You could put 2 factorial if you like. That's just fine. People do that, and that's acceptable as well, as long as you're consistent. So I like to put the actual numbers I'm dividing until they get too big. Or if I'm going to go that large, then I will use factorials if there's going to be big numbers that I don't want to write out. Okay, so most of the time we're not going that far, so it might be more expedient to just go ahead and write the actual value. So here we have the third derivative, and x minus a cubed, and then 3 factorial is equal to 3 times 2 times 1, which is 6. And then it keeps going, and it goes infinitely long. Okay. Now, if a is 0, then this is a very special series. I don't remember, but I think McLaren may have come up with the series before Taylor, and Taylor gave a generalized Taylor series theorem, so he took it further, I believe, and then that's usually the way it happens. A special case comes along, and somebody's able to generalize it to all cases. And so the special case is the McLaren series, and we actually use that a lot, and a lot of disciplines do, engineering and physics as well. Okay, so this is definitely something you want to know. And then we have the remainder theorem. This is also important. So what this is this is saying, okay, we're going to approximate f of x. This is when we want to approximate f of x, because there's no way we can write out this infinite series. So unless we get to a point to where the derivative is 0, okay? And that's another point. So if this is not 0 everywhere, or if all the derivatives are not 0, that would mean that f has to have some infinite factorial or infinite exponent. So there's going to come a point in time when the derivative, well, depending on what kind of derivative it is, it may be 0, okay? But the derivative of 0 is 0. That's allowable. So it meets this all orders of x at a, or x equals a. All orders have a derivative. So even when you get to 0 after a few, so if you're using a polynomial, eventually you'll get to a derivative that's 0. However, if you're using a trig function, you will not necessarily get to 0. So because the derivative of sine is cosine, the derivative of cosine is negative sine, or actually I think I have that backwards. Cosine is sine, sine is negative cosine. I forget, but you can look that up pretty easily. But anyway, it just alternates. Sine, cosine, sine, cosine, sine, cosine. Okay, forever. If you take the log, well, the derivative of the log, natural log, is 1 over x. And then the next derivative is negative 1 over x squared, and it just keeps going. It never goes away. So there are some of these that have an infinite number of derivatives, and we can't write all those out. So we want to say at some point we want to be able to approximate, and there's a whole nother thing about how much error you have, but that's what the remainder is. It's the remaining error, if you will. Okay, so this is the function f of x, the function f of x, which is infinitely differentiable at x equals a. So that's no different than really what we said up here for the Taylor's expansion. We just said it in a different way. So the function f of x, which is infinitely differentiable at x equals a, can be written as a function of a remainder using the Taylor series expansion for some point c. And this is where it gets a little more complicated, and we have to remember this little part here. C is between a and x. Not equal to a, not equal to x. And so whatever point x is, any point x, c is between a and x. Okay? So we write the remainder as r sub n of x. And there's different ways to write this, so I've chosen what I think is the least confusing, but you could use r n minus 1 or n plus 1 as this, but as long as you've defined it, okay? So, but the convention is n here n plus 1 here. So if you wrote n minus 1, then you'd have f of, let's see, f of the nth, f of n derivative of c over n factorial x minus a to the n. Okay, so make sure you're consistent with your notation if you want to do something different. Just write it out so that I will know when I'm grading that you have used this correctly. You're not off by 1 in the index. Okay, so we've got the n plus 1th derivative at c, not at a, at c. This is important. This is different. And then n plus 1 factorial, and then x minus a to the n plus 1. So we've got one of these terms of the Taylor series, except that we've substituted in the derivative is different. And c is between a and x. So what we have here is, this is an important step here, that the remainder is equal to f of x minus t sub n of x. T sub n of x is called the nth degree Taylor polynomial of f of x. Okay, so what that means is, if we say that it's the nth degree, then we are only going to n terms in the Taylor series. Well, n plus 1 if you include 0. Okay, so we're going for the nth derivative, and that's it. That's why if this is the nth derivative here, then this has to be the n plus, then this has to be the n plus 1th derivative. It can't be the same n derivative. The nth derivative, it has to be the n plus 1th, n plus 1th derivative. That's very difficult to say, at least for me. All right. So for some c that's between a and x, we can rewrite the Taylor series as follows. So I didn't write the summation notation, but you certainly could. So this would be f of a plus f prime of a, x minus a, plus f to the second derivative of f at a over 2 factorial, x minus a squared plus dot 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 dot. And now we get to f, the nth derivative of f at a over a factorial times x minus a to the nth power, and then we have the remainder. Okay, so this is very clever to come up with a different value that allows us to stop here. Okay, so I can't imagine the amount of work it took to come up with this. So very clever of them. All right. So let's go over this nth degree Taylor polynomial, and this is a common notation, t sub n at x, okay? But there's other capital T's, so we have to be careful that we know the context here. Now, I've used some notation. If you've taken analysis, you might know this notation. So what it says is f is infinitely differentiable, or infinitely continuous, f is infinitely continuous on the interval a to b, okay? And if x naught is in that open interval a to b, then the nth degree Taylor polynomial at x naught, so instead of a, I'm using x naught. I got these from different sources, so a, b is a nice interval, but we could have made it something else, okay? So different notation. You need to get used to seeing things in different notation. I'm not trying to confuse you, but get you used to this. All right. So f is infinitely continuous. So that means that no matter how many derivatives you take, f is still continuous at on this open interval a to b. And then if x naught is in that open interval, then the nth degree Taylor polynomial at x naught is given by the sum from I equals 0 to n of the ith derivative of f at x naught over I factorial times x minus x naught. Now I could write this, so we could go back to here and we could write this t sub n of x is equal to the sum I equals 0 to n, and then we could use f, the ith derivative of f at a over I factorial x minus a to the I. So we can write it this way if you want, using the same notation that we used here in the Taylor's expansion. Okay? But I wanted to show you derivatives of all orders can be replaced by this notation here. F is in the set, the infinitely continuous set on the interval a to b. Okay, and by that, or family, I'm sorry, infinitely continuous family of functions on the interval a to b. Now, let's do an example. Okay, so this is example 1. We want to find the Taylor series for f of x equals e of x, or e to the x, at x equals 0, and we want to find t4 of x, so the fourth order or the fourth degree polynomial, Taylor polynomial. Okay? Now, so for this first portion, I'm going to make a table. So remember that we have f of x equals the sum. We have I factorial here. We have f raised to the ith derivative at a, x minus a to the I equals 0 to infinity if we're doing the Taylor series. If we're doing the t n of x, I can write it as, I can change infinity for n, which I'm just going to leave as n right now, not 4. And then f ith derivative at a, I factorial, x minus a to the I. Okay? So I have an I factorial, I have an I have a, but that's going to be given to me at 0, so I'm good there. I need, I could put in x minus a, but since a is 0, I'm just going to put in x, and so I need this term x to the x minus a to the ith. I need this term, the ith derivative at a, and I need I factorial. So I'm going to put I factorial next. Then I'm going to put f to the ith derivative at x. I need the x, and then I'll also need the ith derivative at x equals 0, x to the I, and then I'll have the Taylor term here. So the result for each of these, x to the I, because x minus 0 to the ith power is x to the I. All right, so I've got how many? 5. 2, 3, 4, 5, I think. 0, 1, 2, 3, 4. So I only need to there. Okay. And this table is going to help me do this much easier than if I just tried to write it out in terms. You can do that, but I ask you, please don't. That's really hard to grade. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 is 6, and 4 is 24. Now, once you get past 2, you can take this times this, and then this times this. So this is a nice way of doing the factorial, if you will. Okay. So now I need to take the 0th derivative is just going to be f, which is e to the x. Well, it turns out that this is very easy. Every derivative is e to the x. Okay? And so even though I could go further, it depends on what this derivative looks like. If there's a pattern to the derivative, you need to keep going until you can see the pattern. In this case, it's very easy. It's the same. It repeats over and over and over again. Okay? And the interesting thing is, at 0, e to the 0 is 1 for all of these. So we don't even have to show the derivative in this term. And then we want x to the I. And So we're going to have x to the 0, which is 1. We're going to have x to the 1, which is x squared, x cubed, and x to the 4th. Okay? And now I want my Taylor series term for each of the terms in the summation. And so I take, this is always 1, so I need x of I over I factorial. And so this is just going to be 1. And so I'm going to take this divided by this, so I get x. And then x squared over 2, x cubed over 3, and x to the 4th over 20. I'm sorry, it's not over 3. It's over 6. I missed that. So this is over 6 and x to the 4th over 24. All right. So now I can write both answers. So f of x is equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus ... Okay? Since you just need to keep doing this until you can see the patterns, and this, it's pretty clear what the pattern is. Now I want T4 of x, and that is simply going to be what I've written above. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, period. Because I'm saying ended after 4. Okay? Now let's do another example. And for this f of x equals e to the x, we want to find the McLaren series expressed as a remainder with c equal to 1/2 and n equals 4. Why did I do this? Because we've already done most of what we need for n equals 4, right? Because remember that r sub n, or actually, r sub n is equal to f of x minus t sub n of x, right? So I've already got the 4th. I will need the 5th derivative here, okay? But that's going to be pretty easy, the 5th Taylor series term, but that's going to be pretty easy to get. But we're going to do it at 1/2. Okay, so let's write out r sub 4 of x is equal to f, 5th derivative of f, at c, which is 1/2, over 5 factorial. So it's n plus 1, right? So these two are n plus 1. And then we have x minus a, which is x minus 0. So that's x to the n plus 1, which is the 5th. Okay? And so we need the 5th derivative, and the 5th derivative is very easy to get. It's going to be e to the x. Okay, so this is going to be e to the, actually here it's going to be e to the x at 1/2, x equals 1/2, so e to the 1/2, okay. And then we are going to, so here we're going to see e to the 0.5 or e to the 1/2. We've got x to the 5th, and over 5 factorial is 120. Okay? So I could write this as e 0.5 if you like. That's fine. In fact, that's the way I like to write it. So this is my answer for the remainder. And then we know that f of x is equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus e to the 0.5 x to the 5th over 120. This is my remainder. This was T4 of x, and this is R4 of x. And so together they add up to f of x. All right, so this is f of x, this is f of x written with a remainder. Okay, so and now we need to provide the range of x where this expression is valid. Okay, so x is greater than 1/2. So and this is because we had C was between A and X, and so we have 0A is between C, which is 1/2, and then that's between X. And so we take this portion of it, because obviously 1/2 is greater than 0, so this becomes our range. So this portion here is the answer. Okay, so that is what we want. F of x written as find the series expressed as a remainder. Okay, so we're asking for f of x in this question. Now let's look at example 3, and we're going to change from e of x to sine x, and we want to find t5 of x, and we want to find r5 of x for c equals pi over 6. All right. So here we're going to do the same thing we did in question 1. We're going to put I factorial, the ith derivative of f at x, the ith derivative of x, or f at 0, x to the I, and then we'll have our term f, the ith derivative at 0 over I factorial times x to the I. So we're finding the McLaren series here. That's special since a is equal to 0. So we set x naught equal to 0. That's going to be a for us. All right. So now I'm going to need, it says T5 and R5. So I need 0, 1, 2, 3, 4, 5. And I'll even need 6 for Rn. For R5, I'm going to need the 6th derivative. Okay, so 1, 2, 6, 24 times 5 is 120 times 6 is 720. And then I have the function itself at 0, that's sine of x. And then I'm going to have cosine of x. And then I'm going to have negative sine of x, negative cosine of x, then positive sine of x, cosine of x. It's repeating, isn't it? Negative sine of x. All right. So at this point, you could stop here for your Taylor's expansion because you'll see the pattern that you've repeated. But it's really a little better to go at least one more than the beginning of your pattern. And so stopping here really does show that we go sine, cosine, negative cosine, sine, cosine. So we're starting back over. We've done the first two terms. So that's why I chose 5 as my stopping point here. Now, I need the derivative at 0. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is still 0. Negative cosine of 0 is negative 1. And then 0, and then 1, and then 0. Right? All right, so that's our derivative. And then x to the 0 is 1. X squared, x cubed, x to the 4th, x to the 5th, x to the 6th. Now we put it all together. So we have our derivative times x to the I. So these two get multiplied. And then we divide by this column here. Okay. So I'm going to have 0. I'm going to have x divided by 1, which is x. I'm going to have 0 divided by 2, which is 0. I'm going to have negative x cubed divided by 6. Then I'm going to have 0. This one's going to be 0. I'm going to have x to the 5th divided by 120. Okay? So I can now easily write out T5 of x, the fifth Taylor's, let's see, how do we say, the nth degree, so the fourth degree Taylor polynomial. Okay, I want to use the right term. Fifth degree Taylor polynomial in this case. So that is simply equal to 0 plus x plus 0 minus x cubed over 6 plus 0 plus x to the fifth over 120. Okay? So this is our fifth degree Taylor polynomial. Okay? Now we want the remainder, the remainder for n equals 5. And so we're going to take the sixth derivative, which is, so this is going to be f of 6 at pi over 6. So not at 0, so be careful with that. Over 6 factorial, which is 720. Okay, and then x to the sixth. So this is going to be, so we need this term, so negative sine of pi over 6, so this is negative sine of pi over 6 times x to the sixth over 720 equals, this is going to be sine pi over 6, so pi over 6 is, say, here, and so the x, sine is the y, so that's going to be 1/2, okay, equals sine pi over 6. That's a positive, okay, and so this is going to be pi over 6. So we're taking the negative of that, so that'll be negative x to the sixth over 1440. And we don't forget, you have to say where this is valid. So 0c x, and so x has to be greater than pi over 6. C is pi over 6, so x greater than pi over 6. And so this is our answer for that. One more example, I believe. This is the last one. Yep. And so we want to make sure that you've gotten this and that you have a full understanding. So for this one, we're going to find the Taylor's expansion for f of x equals e to the negative x, a equals -4, n equals 4, and then we're going to find r4 of x at c equals 0. So notice that c, if I have a equals 0, c can't be equal to 0 because c has to be between a and x. And so a is -4 and 0 is certainly between that, or we can make 0 between that. So we're going to be valid for our remainder theorem at x greater than 0 for positive numbers. Okay, so we'll do the same. I factorial, ith derivative at x, ith derivative at -4, and then we'll have x minus -4. X minus -4 equals x plus 4. Please don't write it like this or leave it like that. You're mathematicians, so, and you're advanced level mathematicians as far as undergrads, so please write it properly. So this will be x plus 4 to the I, and then we will have the Taylor's series term, each term, -4, x minus I to the I, or x minus 4, I'm sorry, to the I over I factorial. And I'm going to do this for I equals 0, 1, 2, 3, 4, and 5. And hopefully you'll see why I did this once we start seeing the patterns. Okay. So I do urge you to use a table like this. 1, 1, 2, 6, 24, 120. Okay. Now, the derivative of e to the negative, so the original function is e to the negative x. Now the derivative of that is going to be negative e to the negative x by the chain rule. And then this derivative is going to be back to e to the negative x, and then negative e to the negative x, and then e to the negative x, and then negative e to the negative x. Okay? And I want R4, so that's why I went to 5. Okay? So, because I have 4 here. All right. So I could have gone 1 less. All right. So let's make sure I got this right. It'd be that negative, positive, yeah. Negative, positive, negative. All right. So now I have to evaluate this at -4. So e to the -4, please don't put decimals in here. Please leave it exact. Negative e to the -4, e to the -4, negative e to the -4, e to the -4, negative e to the -4. If you want a decimal at the end, great. Otherwise, leave it in exact values, and it's a lot easier for you in this case because those are infinite number of decimals. So you're going to have rounding error if you do anything else. Okay, so to the 0th power, x plus 4 is 1. To the 1 power, x plus 4. X plus 4 quantity squared. X plus 4 quantity cubed. X plus 4 to the 4th. And x plus 4 to the 5th. And now I need this term times this term divided by this term. So I'm going to get e to the -4th. Oh, e to the, I'm sorry, I did all of these wrong. I forgot to put the negative in there. E to the -4 is going to be e to the 4th. All right. So let me just, oops, it's a little too big. All right. So let me see if I can correct this. All right. So they're all going to be positive 4s. Okay, so this is going to be e to the +4, negative e to the 4th, e to the 4th, negative e to the 4th, e to the 4th, negative e to the 4th. All right, so I'm just going to have e to the 4th, and here I'm going to have negative e to the 4th x plus 4, e to the 4th x plus 4 squared over 2, e to the 4th x plus 4 cubed over 6, e to the 4th x plus 4 to the 4th over 24, e to the 4th x plus 4 to the 5th over 120. All right. I don't really need this term. Don't really need it, but we're going to leave it in there. Okay. And so now I need to come up with, I want to write, find the Taylor series expansion for f of x equals e to the -x. So f of x equals e to the -x equals, this is going to be, I'm going to write these terms, e to the 4th minus e to the 4th times x plus 4 plus e to the 4th x plus 4 squared over 2. So this will be minus then e to the 4th x plus 4 cubed over 6 plus e to the 4th x plus 4 to the 4th over 24, and then this will be minus ... Okay, we didn't ask for the nth degree polynomial, we asked for the Taylor series, and so we didn't say as a remainder, but you could do that, but we didn't really say to do that, so this is normally what you would do. Okay, now we did ask for the 5th remainder, and that's going to be at c, and c here is 0. So I'm going to take negative e to the -0, that's e to the x. So this is the 5th derivative. So maybe I should just write out the formula first. So I'm going to have F5, let's see, did I say 5? I said R4. So this is R4. I'm sorry, I've got a notation issue. I was about to say if it's R5, I need the sixth derivative, but it's R4. That's what we said here. So it's R4x equals to F fifth derivative at C, x minus a to the c to the 5 over 5 factorial. Okay, so this is going to be the fifth derivative, negative e to the negative x, but this is at c. C is 0. X minus a, x minus negative 4, x plus 4 to the fifth over 5 factorial, which is 120, which is equal to x plus, let's see, a negative x plus 4 to the fifth over 120, x greater than 0. So let me make this a little neater here. Equals negative. So this is R4, R sub 4. Okay, so that's it for this video. I hope this has helped you. I know it's a long video, but I wanted to take the time to do all the examples, and I hope this helps you remember the Taylor series and have an easy way of doing these problems. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.